Have you ever wondered if you could prove a piece of software is correct? I mean, with the same kind of certainty as a mathematical theorem? Or what if logic itself was a kind of programming language? Well, that's exactly what we're diving into today, a really profound idea called Martin-Löf Type Theory. It sits right at the crossroads of math, logic, and computer science, and it totally changes how we think about what a proof is, what truth is, and even what computation is.
All right, so what's our game plan? First, we're going to look at why we even need something like types. It all started with a big crisis in mathematics. Then, we'll get into the core philosophy behind it all, this idea of constructive logic. After that, we hit the main event, the mind-bending part, when proofs literally become programs. From there, we'll see how all this abstract stuff lets us build incredibly reliable software before we peek into the future of math itself. It's going to be a fun ride.
So, let's start at the beginning. Section 1. Why we need types, or as the subtitle says, how we avoid the paradoxes of the infinite.
I mean, this is the fundamental question, right? It drives this entire field. In math, just one little flaw in a proof can bring decades of work crashing down. And in computer science, a single bug in something critical, think aviation software or medical equipment, the consequences can be catastrophic. We need a foundation that is rock solid, one that doesn't let any sneaky contradictions slip through the cracks.
So, around the turn of the 20th century, mathematicians got a rude awakening. They realized their foundation, what's called naive set theory, was actually broken. Bertrand Russell found this killer paradox. It's kind of like this. Imagine a barber who shaves everyone in town who doesn't shave themselves. So the big question is, who shaves the barber? If he shaves himself, well, he violates his own rule. But if he doesn't shave himself, then he's supposed to be shaved by himself. It's a complete contradiction. It breaks logic, and it proved that you can't just have sets that contain anything without some very strict rules.
And the solution was type theory. So instead of one giant universe of sets, it sorts everything into these collections called types. And here's the crucial move. It creates a strict hierarchy. Think of it like folders on your computer. You can have a folder full of documents, right? And you can have a folder of folders, but you can't have a folder that contains itself. Type theory does the same thing for math. There's a type for simple stuff, then another type that contains those types, and so on, up and up forever. That structure prevents that self-referential loop, and Russell's paradox just disappears. It can't happen.
Okay, so with that foundation in place, we can now explore a totally different way of looking at truth. That brings us to Section 2, the constructive philosophy. And the subtitle really says it all. Truth is something you build.
This slide really gets at a huge shift in thinking. On the left, you have classical logic, the stuff we all learn in school. It says any statement is either true or false, period. Simple. But on the right, you have intuitionistic logic, which is the engine of Martin-Löf Type Theory. And it's way more demanding. It says a statement is only true if you can actually construct a proof for it, if you can provide a concrete piece of evidence. It's not good enough to just show that its opposite is impossible.
So what is a constructive proof then? Well, it's a proof that literally builds the thing it's talking about. So if you want to prove that there's an even number bigger than 10, a constructive proof would just give you the number 12. There it is. You don't get to just say, well, if there wasn't one, logic would fall apart. No, you have to show your work. You have to provide the data. You have to create the object. And this turns proving something from this abstract act of reasoning into an act of construction. And that has massive consequences.
And this is where those consequences just get really, really cool. Section 3, when proofs become programs. This is the big one. This is the aha moment that connects everything we've been talking about.
This whole idea is formalized in something called the Curry-Howard isomorphism. It's a fancy name, but what it describes is this stunning one-to-one relationship between the world of logical proofs and the world of computer programs. It says that, in a very deep and fundamental way, they aren't just related, they're actually the same thing.
Okay, let's make this real. So think of a type as a job description for a program. A logical statement, a proposition like, this function takes a number and gives back a name, that is the type. The proof of that proposition, that's the actual program you write that successfully does that job. So get this. Proving a theorem is no longer just some abstract argument. It is the very act of building a program that works according to the rules. The proof is the program.
This quote from the research just nails it. The world of logic and the world of computation, they're not just running in parallel. They are mirror images of each other. Every single rule in logic has a direct counterpart in computation. That means every proof is a program. And, amazingly, every program is a proof.
So we've got this incredible connection. But so what?
why does this matter outside of a philosophy class or theoretical computer science? Well, that brings us to Section 4, Building Trustworthy Software. This is where we take this beautiful, abstract theory and turn it into verifiable, working code.
And yeah, this whole Curry-Howard thing is not just a neat party trick. It's the engine behind a whole class of incredibly powerful software called proof assistants. These are tools that use type theory to let developers and mathematicians write proofs that a computer can check with absolute mathematical certainty. If your proof type checks, it is correct. End of story.
And we're not talking about some niche idea either. Look at this. There's a whole ecosystem of powerful tools built on these ideas. Systems like Coq and Agda and Isabelle are used today to formally verify critical software, things like computer language compilers, and to prove really complex theorems. This is a mature field that's been around for a long time, starting with pioneers like Automath.
So just how powerful are these things? Well, get this. Researchers have used systems like Coq to build the entire foundation of classical mathematics, the whole shebang, Zermelo-Fraenkel's set theory, from the ground up inside constructive type theory. They can basically build one mathematical universe inside another one just to prove that it all works. That is the ultimate stress test, and it just shows you the incredible power of these systems.
But you know what? The story is still being written. This foundation is so strong that it's opening up brand new ways to think about math. Which brings us to our final section, the future of equality, where we get to explore these strange new worlds. So, the latest evolution is called homotopy type theory, or HoTT for short. It takes all the core ideas from Martin-Löf and adds a completely new geometric way of thinking. In homotopy, types aren't just collections of things anymore. Instead, you can think of them as shapes or spaces, like a point, or a line, or a sphere, or even wilder, higher dimensional things. Now, this new perspective completely flips our understanding of something as basic as equality on its head. In normal logic, if two things are equal, that's it, story's over. But in HoTT, a proof of equality is like a path between 2 points in a space. And just like you can have many different paths to get between two cities, you can have many different proofs that two things are equal. All of a sudden, equality itself has this rich, complex, beautiful structure.
And this is all built on a radical new principle from the late mathematician Vladimir Voevodsky called the univalence axiom. What it basically says is that if two mathematical structures act identically, if they're interchangeable, then for all intents and purposes, they are the same thing. This is huge because it lets mathematicians prove a theorem in one area, like geometry, and then instantly transfer that proof to a totally different area, like algebra, making these deep connections totally rigorous.
And that really brings our whole journey together. We started with proofs as just these logical arguments. Then we saw them become actual programs. And now we see them as geometric paths. Like the quote says, this new world is built on the idea that things are equal if they're structurally interchangeable. This isn't just a small update. It's a completely new, vibrant foundation for mathematics, one that's computational and geometric right at its core. And it just leaves you wondering, what new worlds are we going to be able to build with this?